Hello everyone, welcome back to my channel. So in this video we are going to learn about regular Falsi method. Regular Falsi method, or it is also called as false position method. Okay, so it is also called as false position method or regular Falsi method. Okay, if you are first time to my channel, please consider subscribing and encourage me to do more videos like this. Right, regular Falsi method, so it is also a slower method. Okay, so it is also slower method because we are reaching the true value on one side of polynomial. Okay, but it is faster than bisection method. It is faster than bisection method. Okay, so faster than bisection method, but still it is slower. So order of convergence is linear or first order. So order of convergence is linear or first order. Okay, and the iterative formula. So iterative formula in the case of regular Falsi method is given by x2 is equal to x0 into f of x1 minus x1 into f of x0. So reverse here, x0 into f of x1 minus x1 into f of x0 divided by f of x1 minus f of x0. Okay, so here also it is also an example of interpolation method. Regular Falsi method as bisection method we have seen, so it is also an example of interpolation method only, or we'll call it as bracketing method. Okay, so regular Falsi method is also an example of interpolation method or bracketing method. So in this we'll take two initial estimates, x0 and x1. Okay, so in here this f of x0 is negative. F of x0 is negative and f of x1 is positive. Okay, if we have to take the two initial estimates such that it satisfies this condition, f of x0 should be negative and f of x1 should be positive. And so once you consider the initial estimate, successive approximation is found by using this formula, x2 is equal to this. Okay, and the remaining concept is same as bisection method. So we are going to find f of x2. So if f of x2 is equal to 0, then we can say that x2 is root of f of x. X2 is the root of f of x. So if f of x2 is not equal to 0, if f of x2 is not equal to 0, again we have two cases. Either f of x2 may be either positive or it may be negative. So if it is positive, it replaces the positive root here in the initial estimate, or if it is negative, it replaces the negative root. So we have taken f of x0 is negative, so it replaces x0 here. So now root is bracketed between x2 and x1. Okay, if f of x2 is positive, so it replaces the positive root, so x1 is going to be replaced. So now root is bracketed between x0 and x2. Okay, so this is again we are going to find the successive approximation by using this formula, and we are going to get the next approximate and so on. Okay, same method as we have done in bisection method, but only changes with respect to the iteration formula. There we have taken the average value, but here we have to take this as the formula. Okay, so just only difference between them is the formula usage, and procedure to solve the examples is same in the case of both bisection method and regular Falsi method. Okay, So now we will see an example of how to solve a question using regular Falsi method or false position method. So in this question he has given that find the approximate root of the equation f of x is given for you by using regular Falsi method. Okay, so f of x given for you is x cube minus x minus 4. Okay, so first of all we have to find the initial estimate such that two initial estimates, when you substitute in the f of x, it should have opposite sign. Okay, so I'm taking 0. So when you take 0, it will become 0 minus 4, which is equal to minus 4 you'll get. Right, so I'm taking 1. So when you take 1, what you'll get? 1 minus 4, which is equal to minus 4 only. So root does not lie between 0 and 1. So I'm taking 2, f of 2. So you will have 2 cube minus 2 minus 4. 2 cube is 8. 8 minus 6 is 2, which is greater than 0. This is less than 0. Therefore, root lies between 1 and 2. Okay. So therefore, root lies between 1 and 2. Okay. So now it is bracketed between 1 and 2. So by false position method, the iterative formula is given by x2 is equal to x0 into f of x1, x0 into f of x1 minus x1 into f of x0 divided by f of x1 minus f of x0. Okay, so first of all here x0 is equal to 1, x1 is equal to 2, f of x0 is equal to, that is f of 1 is equal to minus 4, f of x1 is equal to 2. Right, so I'm substituting all those values here. X0 is 1 into f of x1 is 2, so 1 into 2 minus x1 is 2 into f of x0 is minus 4. Okay, divided by f of x1 is 2 minus of minus 4. So if you find this value, you'll get as 1.666. Okay, so and again you are going to find f of 1.666. f of 1.666, how can you find? 1.666 whole cube minus 1.666 minus 4. Okay, so if you find this value, it will be around minus 1.042, which is less than 0. So when it is less than 0 and its value is negative, it replaces the negative root. So what is the negative root here? 1 is the negative root. So 1 is replaced by 1.666. So now the new root is bracketed between 1.666 and 2. So if you observe here, from the initial estimate to the first estimate here, so the gap between the estimates are going to be reduced. Okay, same as bisection method only. Now again, this is 1.666 and 2, so we have to find x2 again, the approximation. So x2 is given by x0, so now x0 is 1.666 and f of x0 is minus 1.042, x1 is 2 and f of x1 is also 2. Okay, because f of 2 value is 2 only. Right, so substituting all those, we have to find the x2 value. So if you find that I am taking that as x3 instead of x2, so x0 is 1.666 into f of x1 is 2 minus x1 is 2 into f of x0 is minus 1.042 divided by f of x1 is 2 minus of minus 1.042. Okay, if you take calculator and solve for this, you will get 1.780. Okay, and f of 1.78 is, so if you solve that, you'll get minus 0.1402, minus 0.1402. So it is a negative value less than 0, so it replaces the negative root. So it replaces the negative root. So what is the negative root here? So in these two, what is the negative root? 1.666 is the negative root. So 1.666 is now replaced by 1.78. So it is coming closer still. So the now root is bracketed between 1.78 and 2. 1.78 and 2. Okay, so f of 1.78, what is f of 1.78 is minus 0.1402, and f of 2 is still 2. Okay, so next approximation, x4 is given by x naught. So this is x naught now. X naught is 1.78. So x naught is 1.78 into f of x1. F of x1 is 2. So 1.78 into 2 minus x1. X1 is 2 here, and f of x naught. F of 1.78 is minus 0.1402 divided by f of x1, 2 minus 0.1402. Okay, so if you find this value, you will get around 1.794. And if you find f of 1.794, so you'll get around minus 0.0201. So I'm writing directly the values, but you solve, okay, using calculator. 0.021, which is less than 0, because I have already solved this problem. So minus 0.0201, which is less than 0. So this value is less than 0. Now it replaces the negative root. What is the negative root now? Again 1.78. So 1.78 is replaced by 1.794. Okay, so now the root lies between 1.794 and 2. Okay, so f of 1.794 is minus 0.0201, and f of 2 is equal to 2. Okay, so the next approximation, x5 is given by so this is x naught now. So x naught is 1.794 into f of x1. F of x1 is 2 minus x1 is 2, f of x naught value is this, minus 0.0201 divided by f of x1 value is 2 minus of minus 0.0201. So if you find this value, you'll get around 1.796. So f of 1.796, if you find, it will be around minus 0.0027. Okay, still it is less than 0. So now the root is bracketed between 1.796 and 2. 1.796 and 2. Okay, so if 1.796 and 2, we'll find one other root. So 1.796 in 2, then f of 1.796 is minus 0.0027, and f of 2 is still 2. So x6 I am finding. So x6 is x naught. X naught is 1.796 into f of x1 is 2 minus x1 is 2 into f of x naught is minus 0.0027 divided by 2 minus 0.0027. Okay, so if you find this, you'll get around almost 1.796. So iteration stops here because two successive iterations are same. Since x5 is equal to x6, we can stop the iteration, and therefore root of f of x is 1.796. Okay, so this is how we can solve an example using regular Falsi method. So for any given equation, first of all you have to take the initial estimates and corresponding successive approximations are found by using this formula. So while you are finding the successive approximations, we will reduce the gap between the estimates. So for each and every successive approximation here, so we are reducing the gap between the estimates, and iteration stops when two successive approximations will have the same value, like this 1.796 in this case. Okay.